this is a topic talk. So I will try to be as basic as possible. So I apologize for those who are experts in this subject. So here is the structure of this talk. I will start by basically reviewing briefly the standard model, the basic equations that go there, the basic parameters, not all the parameters, but the basic parameters of the model, review what's a Friedman equation, etc. Then I will briefly discuss there are many tensions, of course, in the standard model. I will try to focus and discuss briefly the three, what I consider, and most people actually, the main tensions of the standard model, which is the Hubble tension, the so-called growth tension, and the cosmological principle cosmic dipole tension, which seems to put into some constraints, introduce some possibilities for new physics coming through this into a new model possible. Then I will focus mostly on the H0 tension and describe in some detail how does this tension emerge. This will be an overlap with my previous talk that I had in this room a few days ago. Then I will discuss the classification of models and the gravitational transition approach. How does this one particular class of models enters and how it comes to the other models. So let me start with reviewing a little bit the standard model and seeing what are the basic assumptions. Now, the cornerstone of cosmology, and of course also the standard model, is of course the cosmological principle. Okay, that the universe as a whole is homogeneous, isotropic, described by this metric which is called the FRW metric. And basically there is one function that in cosmology is the basic question how to measure the scale factor A of t. This is one of the main goals of cosmology, is to measure this function and actually find models which can be consistent with this particular function. But first of all, of course, we have to assume that this metric exists. And recently there has been one of the tensions actually if this metric is actually the correct metric. That's a question. And it has been questioned by some people. So, but still, the standard model is this metric. The second assumption of the standard model is general relativity. It's assumed that Einstein's equations describe gravity correctly. And so these Einstein equations are expressed in the context of this metric through the Friedman equation. One of them is this one, which gives us the Hubble parameter in terms of the contents of the universe. The curvature, of course, and the density of the various components of the universe. So if we measure this A of t, and can go ahead through this equation and measure the properties and the evolution of this rho as a function of the scale factor A. So we get information now from geometry, you go to microphysics, to physics. And that's amazing. That's why we say that it's an interaction between particle physics, which is hidden here, and cosmology, which is hidden here through the Einstein equation. Of course, one can say that maybe general relativity is not valid, and since this part of geometry may be changed, you may have a factor of h cubed, for example, or something else on this side. Or alternatively, particle physics can tell us that there are more particles than we thought, or more types of energy than we thought, and so in that case we change this. But this equation allows us to test both particle physics, field theory, and geometry, cosmology, and the geometry of the universe, and the gravity theory, gravitational theory. Now this is the second Friedman equation. You see pressure enters of the quantities of the universe, of the ideal fluid. There's a minus sign to tell you that if you want to have acceleration, you must have negative pressure or negative energy density. And these equations, how the, as I will say, there is indication of accelerating expansion. And of course, here is the cosmological constant, which you see comes with a plus sign, which means that a positive cosmological constant induces acceleration, which is consistent with the observations that have been present during the last 20 years. Now, if you know, now this equation here is the continuity equation, which actually gives us information about how the energy density evolves with the scale factor, provided that we know a relation between P and rho, the equation of state of the fluid. So this system, which can be supplemented, two of them are independent. If we supplement it with an equation of state, a relation between P and rho can give us this rho of A from this equation. And so we have a consistency condition through this equation. For example, for matter, we have that matter redshifts as a to the cube, a to the minus 3. But other types of which have pressure equal to 0, if we put pressure equal to 0, we get this equation, but other types of equations can give us different kinds of evolution. Now, the components in the context of the standard model are just the known particles. That's the minimal assumption. What you have, we have regular matter. Okay, this is the matter density parameter. It's actually the ratio between the density and the critical density. For critical density is this function here, is the density that we would have in the context of flat universe. So this is omega here. So for matter, this is the present ratio rho over rho critical for matter, and redshifts a to the minus 3. We know that the particles around us. We know that most of the matter is described by particles, and probably dark matter is also described by particles. At least we know that probably it's this way. Radiation goes like a to the minus 4. We have, in that case, we have a equal to 1/3 rho with this equation of state. This is the cosmological constant contribution, which is doesn't change with the redshift, and this is basically the standard model H. This is the present day of the value we have the parameter, which is the thing that we want to measure in many cases to test which is one of the parameters of the model. So at least the model has these parameters: H naught, omega 0 radiation, omega 0 matter, the curvature, and the cosmological constant, but these are related, of course, they have to sum to 1 because of consistency of this relation. For if you put H equal to H naught here, you get a consistency, and A equal to 1, you get a consistency relation. So there are at least 3 parameters here which are free for the model. There are more parameters, of course. Now, for the redshift is, we can measure somehow the scale factor at the time of emission of the radiation through the redshift, and taking advantage of the fact that lambda is the wavelength of radiation that reaches us, scales like the scale factor. You can show this from the geodesics of photons. And so there's a connection between the measured redshift, the detected wavelength over the emitted wavelength, the emitted wavelength over the detected wavelength, which goes as like 1 over A to T, and it's equal to 1 plus Z, where Z is the redshift, that is the ratio of minus 1 of the wavelengths. So redshift can be very well measured. So if we can measure redshift, okay, then we actually have the scale factor at the time of emission. So if through redshift can measure but what's the time of emission? This is the way to make alpha D. We need also the time of emission. That we can obtain only if we measure the distance. That's why the A of T requires measuring both of A, and that's very easy to redshift, extremely easy, just measure the redshift. But you also want to know the time when this thing was emitted to find A of T. And this time can only be obtained if you measure the distance. That's why a critical way to measure this function A of T is to measure distances to various objects which emit the light, and then you measure the A, and then you measure the distance or the time when it was emitted, and then you have the function A of T. But how to measure distance? That's a very difficult thing. In any case, what I'm going to use here is the usual form in terms of the redshift, H of Z squared in terms of redshift. It's just put 1 over A equals 1 plus Z in this equation, and you have this general equation for the standard model. And the question is this equation here valid? Do observation support this equation? That's the basic question that we want to ask. And the key problem is the following, that unfortunately there are various measurements which measure different values for H naught. Also different values, for example, for omega matter. This is called tension. If you measure using the CMP data a value of H naught, and using, for example, local measurements of distances, a different value, which is not consistent, you have a tension for H naught. This is called the Hubble tension. Similarly with omega matter. If we measure omega matter using geometry to one value and using growth of fluctuations, gravity, and another value, it's another tension. Means that either the gravitational part is wrong or the geometrical part is wrong. Maybe another theory or some other ingredient. So tensions are the disagreement of the parameter values, basically parameter values among different measurements. And the first and most important tension we have is the so-called Hubble tension. The Hubble parameter is, I would say, the most important parameter of cosmology. It tells you how rapidly the universe expands now, at the present time. And nothing more fundamental than that. And that thing, unfortunately, the most basic thing, we cannot measure. We can measure other things extremely accurately, but this thing, look at this. This is the value of H naught obtained from the cosmic microwave background, extremely accurate. Extremely precise, I should say. It's not accurate. It's precise, but not accurate. We don't know if it's accurate. Maybe it's accurate, but it's not obviously accurate. And this is also relatively also precise. One of them has to be not accurate. Even though both are precise, one of them is not true. It's not accurate. So you see that like, some measurements are gathered in this direction, those that are based that are related to the CMB, others are close to this value, which is obtained from distances using the Cepheid calibration, as they told. So these are local measurements, and these are measurements based on the CMB that we all know. Now, this is also this proof has been shown many times in this meeting, but since this is a public talk, I would have to show it again in case there are people who are not done that. And you see that the precision of H naught, which is on this axis, on the horizontal axis, is different for different measurements. These are measurements based on early times, on the CMB, the standard rulers, as I will discuss, and this is late time measurements obtained using local calibrators. So the question is, how can we actually group this? Why is this disagreement? What are the properties of these measurements we like this kind of value, about 67 kilometers per second per megapascal, compared to these measurements, which give the other value? Is it just that these are late time measurements? Because some of them are also favoring this value, small value, or is it something else? That's a question that we have to think. Yes.
What's the third family?
This one?
No, below the last dashed line.
This one?
Yeah.
This is actually a combination of some of various other measurements. So these are different distinct measurements. So if you combine selectively some of them and combine them, you get this. But so this is not really.
It's not independent.
It's not independent from the others. It's just a combination that some measures people have done. So probably it shouldn't even be there because it really mixes things. But anyway. So this is the so-called Hubble tension. And you can see a review of all these tensions, including the Hubble tension and many other tensions, in our recent review, which was published in Astronomy, where we actually give a global discussion of not only the Hubble tension, but all the others that I will discuss later on. Now, the second tension is the so-called growth tension. The puzzle is the following. If we use the parameters that geometry gave us for the standard model, the omega matter, and for example, the H node and all the other parameters. This was a standard model. And we actually try to measure the rate by which perturbations grow and compare with observations that directly probe this growth of fluctuations, like how many galaxies we have, what's the correlation factor of galaxies, what are the peculiar velocities. We find that the growth that we measure directly is about 3 sigma lower than the growth that we would expect in the context of generativity, standard model. And this strength of this growth is expressed through this parameter called SA, which is the product of this sigma H, which is essentially a normalization. It's actually the amplitude of fluctuations on scales of 8 megapascal present. So the larger SA, the more growth we have, because you have more fluctuations on the average RMS on scales of 8 megapascal, times omega zero matter, which also favors higher growth because the growth is actually probed by matter. It's also generativity. So this product gives you an estimate of how efficient the growth of fluctuation is. And so you see this, the degeneracy along this line of constant sigma f. You see this, if you write this constant sigma line, it goes to something like that, like a hyperbola roughly. And so you see there's a degeneracy here. So if you are on this side of this hyperbola, means stronger growth. if you are on close to this side, actually you miss weaker growth. So you see that this point of the CMB obtained from the cosmic microwave background parameters for general relativity gives you a predicted higher growth, higher sigma, higher S8, while the actual measured S8 in the context of peculiar velocities, the so-called redshift space distortion, we measure effectively the velocities of various galaxies using the redshifts and the difference from the cosmological expansion. You see that they are lower. So the measurement gives lower S8 than the expectations from the geometry, from the cosmic microwave background, from directly measuring these parameters. So this is a problem. This is the case for this measurement using peculiar velocities, the so-called redshift space distortion measures redshift space changes. Also, we can do the same with weak lensing. Again, the same problem. You see that this is obtained from Planck, from the CMB. And this is the actual measure from weak lensing, which probes the structures and the number of essentially classes and number of the strength of clustered structures through of dark matter using weak lensing. And similarly, we can do the same using cluster counts. Again, the same problem. You see this hyperbola here, measurement is actually lower than the expectations from Planck, from the directly measured from the series. So all these three classes of measurements seem to support a 2 to 3 sigma weaker growth, lower S8 than expected. Does it mean that we need a different theory of gravity, which have a lower growth? Does it mean that we have another component of energy which somehow smooths out fluctuations? We don't know. And things have become even worse recently because a different probe, the James Webb Telescope, which measures galaxies at early times, redshift about 10, showed the opposite. So stronger growth at early. These are late time growth. Okay, this is up to redshift about 1 to 2. At redshift 10, the Webb Telescope found more galaxies, more stronger, more big galaxies, more massive galaxies than expected. So it looks like on this redshift it goes the opposite way. So these are some puzzling things which may be due to some systematics, but maybe also due to some peculiar physics change. Some gravitational change strength from early times to late times is one possibility.
Yeah. Not only the value, but you see that the correlation between sigma and omega is also changing. And then
this is an approximate combination which gives you the degeneracy direction. So it's overall it's not always valid for all measurements. Maybe some other this power for example omega may be a bit different for different measurements. But overall, this is the if you have big sigma and big omega matter, you have more growth. Now, the exact powers may vary depending on the observation.
So the direct measurement says that omega more is sigma is small.
Yeah, of course. That's because this is degeneracy. I mean, the measurements are sensitive not to each one individually, but to their product. Now, the product to some powers, of course, and these powers may be slightly different. It's a matter of how you measure things. It's not something inherent. And so, the third class of tensions is the so-called cosmic dipoles. Not only do we have problems with the dynamics in the context of the cosmological principle, but also we found very big deviations on very large scales, which are inconsistent with what this model would predict. One example, for example, is the back flows. When people try to measure in the various surveys using redshift measurements and their deviations from the Hubble flow, the mean velocities in various volumes. Let's say we take a 300 megapascal volume and we measure the mean velocity in the context of various surveys. We found that these bulk flows increase with the scale of our box of our averaging. Not only increase, but they are also much bigger than the prediction of the standard model. So it looks like we have much more velocity than expected, but also we have a wrong behavior of measurements compared to the expectation. As you go to, in the context of the cosmological principle, if you go to very big volumes, you see less anisotropy. These people here, published in 23, they see higher velocity and increasing. Very peculiar kind of measurement, and that has created, in fact, many sigma away from the expectation. The probability for consistency is much less than 0.01, especially in this model here. 0.00021 is the probability that these two is a statistical fluctuation. That's a puzzle. In addition to that, there is the so-called QSO dipole, which we had an interesting talk yesterday about this, which actually shows that the distribution of quasars in the sky is expected to be somewhat anisotropic because of our peculiar velocity with respect to the cosmic frame. And but what we find that this anisotropy is much bigger than the expected. See this probability distribution for the dipole. This is the dipole of the distribution of quasars in the sky. We expect some dipole because we are moving with respect to the mean to the CMB frame. We are moving in some direction. So if you are moving due to Doppler shift, you see more galaxies direction you are moving compared to the other one because of the intensity. We have larger intensity due to the Doppler effect in front of you and behind. Also the angle change. So you expect some dipole, and this is the dipole you expect based on the CMB velocity, and that's the dipole people find 5 sigma change. So it looks like either the velocity we have from the CMB is completely incorrect, or it's very unlikely, or there is an intrinsic anisotropy of quasars, which is much stronger than expected. And quasars are talking about very high redshift. So this is a redshift that the ΛCDM cannot really say anything about anisotropy. It should be smooth. Quasars there should be overall a very isotropic function. And here you see the directions. It happens to be close to the dipole. That's a puzzling thing because it's puzzling because it's the same direction of our velocity, even though probably these two effects should be unrelated. If there was an intrinsic anisotropy in the universe, why should it have the same direction as our velocity with respect to the CMB? It's a puzzling question, but this also remains a very interesting point. Also, we have the radio dipole, which is the same effect as the QSO, but also plotted for the radio galaxies, which are also at high redshifts. And you see here, this is the expected value from our CMB velocity. These are based on two different surveys. This is a theta equal to 0 measurement, takes the whole sky. If you subtract various parts of the sky, some slices of the sky, you get somewhat small, but it's a close theta dependence, so it's what we expect to get. So these points correspond to masking some points of the sky and seeing how that is behaving with theta. If you mask some slash of the sky with the value of theta, you get somewhat smaller. We get this cosine. It's a real dipole, it looks like. It has a cos theta behavior. So these are the dipoles overall that have been. This is from this very nice review, which has been written recently. It combines all the data about anisotropy that we have. And you see, for example, that this is the direction of the QSO dipole. This is galactic coordinates. This is the radio galaxy dipole, which is reasonably close. And this is the dark flow. The bulk flow dipole is this one. Now, there has been a previous claim about some huge scale velocities. This is controversial, that's why I didn't mention this, which also indicates that even in very, very large scales, we have a similar flow of velocities, which is similar to this one, but this has been under various debates about its validity. It was not being confirmed by other studies, so this point is not so accurate, probably. But anyway, it also has to be referred along with the other cases. And you see that all these dipoles are more or less close to each other in this part of the sky. So the question is there some relation between them? So we have a lot of tensions, 5 sigma tensions, 3 sigma tensions, this completely very large amount of. Why could we still have ΛCDM as our standard model? I mean, the previous model, SCDM, which are only called dark matter, went away with much smaller tensions. It was replaced with much smaller tension than this one. And we have such huge tension, this thing is still there. Well, most of us, if you ask, take a poll, believe ΛCDM is the most probable model, even though we're looking for alternatives. Why is it still our standard model? Let's try to think about this question. The first reason is inertia. Okay, we have all been working on lambda CDM, or at least most people have been working on lambda. We have done results, important results. I mean, and it has indeed many successes. These are the intentions, but there are many other successes, of course, so we cannot really ignore them. So the human factor tends to be conservative. Most people are working a lot of time on that. Why should I change model? I mean, I worked a lot on that. This is an important model. So it's a simple also. The second is that, and most important, there is a lack of a simple alternative. There are lots of alternatives, but with many parameters. And not only parameters, but also not justified parameters. I mean, they are arbitrary. Put a scalar field and a potential. Even if it's the correct model, is it really a model? There's an issue. Lambda CDM was a real model. Lambda is a generic thing. It's the vacuum energy, the energy of the vacuum. If you have a vacuum field theory predicts that you must have some kind of cosmological. Now it's much bigger, of course, but it's something that we know it has to exist based on quantum field theory. Now, also there are too many tensions, and they pull in different directions. It's difficult to compensate all of them within a single approach. Now, let's compare with the previous other model changes to see what happened before. First of all, initially there was this so-called steady state model, which went to the Big Bang model. And that was, of course, efficiently done because of the data based on the CMB. And there was a simple alternative. I mean, there was the Friedman equations and the Big Bang theory. It was a very clearly well-defined and simple alternative. Now, from SCDM, the model that we had before, the flat omega dominated flat universe, having only matter and radiation, we went to additional component of cosmological constant here. Now, the reason was that we had data and a simple alternative to the cosmological constant. We had a simple alternative, very simple. And there was this studies here, even this was initially pointed out by people in 1984. Then the start in 1990 pushed towards lambda CDM initially, even though there were very few tests at that time. Then we had Krauss and Turner. And the very weak evidence for that was basically the age of the universe, the matter power spectrum, which showed some inconsistency at the times, and the peculiar velocities, which also were not as large as it should be. So very weak evidence, and yet this model was gained very quickly momentum. Of course, in 1998, it really, after this 3-4 sigma, 5 sigma discovery of supernova, actually was replaced. And the question is, what is the new simple replacement of lambda CDM that will release most tension with just 1 or 2 parameters, which should also be, of course, physically motivated? Just that putting 2 arbitrary parameters, one should actually put physically motivated parameters. But at least, even if they're not physically motivated, at least there should be a parameterization that does this job. So to actually find which are these 2 parameters, we need to understand deeply the data, first of all, and not only one data set, but many data sets, and also to understand the origins and assumptions hidden in the tension. If we just say, for example, H naught is different, that doesn't say much. We have to understand why each observation predicts different H naught. What are the inside ingredients that is involved in this observation? Otherwise, it's not so. We're not design right models if we don't really understand the observations exactly how. What are the assumptions hidden in each observation? So this brings us to the cosmological distance and the cosmological. So let's see, how do we measure the H naught, for example? For that, we need to measure the cosmological distance, and especially we need to measure. We need some standard method. The best way to do that using luminosity distance and standard candles, which standard candles could be, for example, the supernova type 1A and the GRBs. Here you see a mechanism of presentation for supernova. We have for example, it could be a star which has a companion and eventually crosses the Chandrasekhar mass limit and eventually explodes to supernova after accreting some material from the companion. And then it explodes with an absolute luminosity which is standardizable, at least it can be known. We measure the intensity locally in the telescopes, we assume that L is standardizable from the supernova, and then we measure the distance, which is actually the luminosity distance, it's called luminosity distance, and is related to the intensity by the power emitted over the whole area of the sphere at this distance. And this gives us essentially this distance. So we can have very standard canals. This type 1A supernova, which are seen at very large distance. The Cepheids, the GRB, which are also seen at very large distance. And so we can actually use this measurement to. Now, in a flat universe, this luminosity distance in the cosmological setup is related to the Hubble expansion in this way. But in a Euclidean space, of course, it's the usual distance. Now we're in cosmology, so we use this relation there. And for supernova, we have this redshift range, which is measured up to 2.6. For GRB, we can go up to 8 or 9 redshift. And but this is not a very good standardizer, so there's a problem with GRB. So if we measure this, we have various values of this integral, and we fit this with a chi-square, and we measure this h of z at various redshifts by essentially measuring this integral at the various redshifts in the context of a parameterization or whatever. Now, astronomers tend not to use so much the apparent and the absolute luminosity, they use the apparent and absolute magnitudes, which are related to these luminosities using this equation here. So it's not this equation that is used, but it's something similar which uses these magnitudes instead of the luminosity. Now, a similar way to do the same measurement, a similar measurement of h of z, is using the angular diameter distance, using standard rulers. And the most useful standard ruler is the CMB sound horizon, which you see here. But we can measure now it's an angle to an object which has a known size. In this case, the sound horizon. That is the distance sound waves travel from the Big Bang to the time of recombination. And so if we measure this, if we know this, because we can find this using CMB physics, and I will show you later how, we can measure this angular diameter distance, which in the context of a Euclidean space, it would be the actual distance, but in the context of expanding universe, it is so we have dA is Rs over theta, Rs is calculable, theta is measurable, and dA then for is obtained and is connected to h of z using this relation that Celia also showed in her talk just in the previous hour. So we can use Barnard to. So what standard rulers we have? Many of them, but the most interesting are the Barnard acoustic oscillations, which has z equal to about order 1, and also the CMB spectrum, which is the sound horizon recombination that will be about 1,100. Now, how do we do that in practice? We first have to standardize supernova using Cepheids stars, which are stars which are supergiant stars which are pulsating, and therefore they have connection of their luminosity with their period. So we can observe them at small distances within the galaxy, calibrate them, find the slope of this line. Using, if we measure this with geometrical methods, we also measure this. We can find this line. So that means we calibrate them. And then we have similar stars on higher distances where we only can find the period of oscillation, the period of the oscillation. Then we can induce luminosity. And so we can find the distance to further galaxies. Now, this is so we calibrate Cepheids locally using parallax methods. That is using, for example, the angle, how do they change, how do they move in the sky as the Earth rotates around the Sun. And then we use nearby, after we calibrate them, we can find their distance in nearby galaxies where they also host supernovae. And in this way, we can actually calibrate also supernovae, see how their luminosity change based on their properties. In this case, the properties are the light curve, how fast it drops, and how fast, how thick it is, and what's the color, for example, of this emission. So we standardize then supernovae, and then we use supernovae at more higher distances, and we find the luminosities to these supernovae using their absolute luminosity. So use calibrated stars to calibrate supernova at nearby galaxies, and then use this calibrated supernova at distant galaxies to find H0 and H of Z. This is the most efficient method we have right now to measure H of Z. It's very accurate. It's very precise, actually. It's probably is also, most people think it's also accurate. Now, another calibrator apart from this F5 is the so-called tip of the red giant, or which is also a red type calibrator. This is the HR diagram. And there is a tip up here. So this is the evolution of stars. This is the essentially the color of stars. This is their luminosity, which is plotted according to number of stars in its region. And you see that in this corner here, this is a characteristic set of stars which lie in this corner, which are the stars which start burning helium. And these stars are called red giants at the tip of the HR diagram, tip of the red giant area. And these stars are supposed to have, might be shown that they have a standardized absolute luminosity, so we can know their absolute luminosity. And then using this common property they have, that is they have just exhausted hydrogen in their cores and have just become helium burning, so they have a common feature, so that means that the luminosity could also be similar, or at least standardized. And so their brightness can be standardized, and they can serve as an alternative bright Southern calculus of the Cepheid stars. But this is also a very accurate probe. It gives an H naught, but it's an H of Z, but it's not in full agreement with the Cepheid. It's in good agreement, but consistent, but not in full agreement. So how does this game is actually played? Now let's go to the real game, because so far we have been talking about more or less qualitative things. So we're now going to see how it's actually being done. How do we fit standard calculus for H naught for Z less than 0.1? We start with this relation which connects the apparent luminosity, the apparent magnitude in this case, with the absolute magnitude, which is the absolute luminosity, with the luminosity distance, and this part has to do with the megaparsecs here. So this is the key relation. This is like the L equal L capital over 4 pi dl square, but it's written in terms of magnitudes rather than luminosity. So we measure this at various redshifts. We assume that we know this because these objects are standard calculus. This is the absolute luminosity, and then we infer this for various models. And inside this is hidden the Hubble parameter as a function of redshift. So if we use this expression, dl in terms of H of Z, define this Hubble free luminosity distance, because this has an H naught in the numerator, it cancels the H naught that should be here in the denominator. And then we obtain this relation, which connects again the same quantities. And we see there's a degeneracy between M and H naught. It's a new parameter here, which this is what can be measured, which is the parameter which connects the two, the value we're going to find. So this can be written in this way. This is the measured part. This is the parameters to fit, and this is the combined two constant in a single constant. Since it's a constant, these are degenerate in a single constant. And so we measure this, we measure this locally from the Cepheids, and then we actually infer this this H naught here by assuming for small z that we can use a cosmographic expansion for dl of z, and we can either fix this Q0 here or fit it along with the other parameters. So the parameters to fit here is, assuming that this is measured locally, is the Q naught and H naught. And the crucial thing is that we have to measure this locally. If you don't measure this locally, you don't measure H naught, because you cannot distinguish this from M. You can only measure this combination. But you have to use Cepheids to measure the luminosity, to standardize the luminosity, the supernova, and then once you know M, you can find H naught. So that's a crucial point. So there's a degeneracy between them which breaks according to this, if we do this measurement. Now, if we want to measure other cosmological parameters, we have to go away from this expansion to go to the real model. This is an expansion around Z equals 0, which is valid for any model. So approximately this is the deceleration parameter Q0. And we can use this unjudged for h of z at larger distances to find the full parameters. We can make a chi-square minimization, or we subtract from the observation the theoretical prediction for m. And the theoretical prediction is obtained from this DL, from this ΛCDM expression for m to theta, m of theta, and you see only the m calligraphic enters here, which is the combination of h naught and m. That's what on cosmology we can only fit this one. With astrophysics, we fit this and this separate. If you don't use astrophysics, no way to find h naught. So if there is a problem with the measurement of h naught, it's a dirty problem. Why? It's hidden in astrophysics. Because we have to understand how you measure this one. If you measure this wrongly, of course you get a wrong h naught. Because the only thing to measure cosmologically is this combination. But with surface astrophysics, you measure this one. It's quite possible that this is an issue of dirty astrophysics at very low distance. Another way to measure h0 and h of z is using gravitational lensing. It's completely independent. What you do, you see at a lensing cluster, for example, and you see the images of background galaxies due to lensing of a galaxy lens cluster. And you measure now the angles to the various images, theta A and theta B. You have the true angle to the true source. You have these luminosity distances, this distance from the source to the lens, from the observer to the lens, and then from the observer to the source. And as you observe this background galaxy, you notice the following, that as this is changing, maybe there has some luminosity changes, these changes do not follow the same, do not occur at the same time for these two images. There's a so-called time delay. One image changes slightly with some delay with respect to the other image. And so this time delay can be solved, can be measured, and can be connected with the Hubble parameter of the Hubble parameter of the expansion. How? This is the relation. It connects the time delay of the images with the luminosity distances. You see that if we put here the actual form, you see that this ratios are proportional to 1 over h0. And here also we have the lensing potential. This C of theta is the potential of the lens, which must be modeled, the difference, of course, among the images, which must be modeled in order to obtain this h naught. So you have to know here very standard. You have to know the redshift of the lens, of course, the angles which you measure, but you also have to know the potential of the lens. And this is also systematic, which this is one of the measurements that I showed in the first slide, which shows that we can measure it with very independent ways. Of course, you should notice here that there is nothing here about the potential, which has to do with gravity. So gravity here, the laws of gravity plays a role. But it's important to know that this depends on the diameter. Another way to do that is to use gravitational waves. What is being measured is the amplitude of the gravitational waves, and this can be connected with the gravitational luminosity distance as one over the other times some parameters here, which is this is the frequency of the gravitational waves, and this is the so-called chilling mass, which has to do with the masses of the binaries that produce the gravitational waves. And there is this assumption here that we have a binary, for example, Newton's binary, which as they coalesce, they produce some gravitational waves, and at the same time, sometimes it may happen that light is emitted because of this process. We may emit and find the source of this galaxy, the redshift of this galaxy, and if we can actually measure the distance from this relation, and if it happens to be that there's also some information about the redshift by detecting light from this event, then we can have a combination of D and Z, and we can actually measure the Hubble constant. So if we can measure both the distance and the redshift, in that case, one can find the Hubble parameter. And here's a somewhat old example of this measurement. Now there have been more accurate measurements, but still they're not competitive. So this is the measurement of local measurement of the Suz et al. with the Cepheids. This is the CMB measurement. And this is the measurement that was made with standard science, which we had also information about the redshift and also about the distance. And we see there is a huge redshift, but a huge error, a huge uncertainty, but it's potential in the future this may change if we find more standard science. So this is another way to measure the Hubble constant. Now the most accurate way actually we have so far to measure the Hubble constant is using the standard ruler of the sound horizon recombination. This gives us an extremely small error, smaller than all other measurements. But it also has some assumptions hidden in it, and let's see actually these assumptions. So we can use this sound horizon recombination as a standard ruler. We can measure this theta to this standard ruler from the CMB spectrum, angular power spectrum. This is measured. We can this from these peaks of the standard. So we change somewhat the theta. For example, these peaks change. So here's an example. If you change it by 8%, this is the difference in the peaks. So you see that it's sensitive to theta. Also, we can measure this theta using the baryon acoustic oscillations. This feature that we have in the spectrum as due to the south horizon, the baryons that remain after the recombination. I will show that afterwards how this emerges. And then we can also calculate this RS. It's not measured, it's calculated based on some assumptions. What are these assumptions? We use this RS, sound horizon scale, which is the distance traveled by sound waves from the Big Bang to the time of recombination, expressed this way in terms of the Hubble, in terms of the scale factor, and how you can estimate what should be the scale factor during this period by assuming, which depends now on the density of baryons, the density of photons, and the density of dark matter. So it can be calculated. And then we can go to this standard ruler relation, which relates the angle theta s with the standard ruler comoving or physical size, and divided by the comoving or physical size of the angular diameter distance. And for example, in the case of this calculation, one can show that the favorable value is about 147 megaparsecs in comoving coordinates. This dA of z can also express in comoving form in this form. So it's from 0 to z. dz, E of z is the Hubble-free expansion rate, with the dH naught that should multiply this goes up to the numerator. So it's h naught times Rs over this integral. Now from the peaks of the CMB, we can estimate the value of omega zero matter. So we put it here. Rs we have calculated, and since theta s is measured, we refer h naught up here. And you see that this product here is somehow degenerate. And also this degenerates with this. So if we made an error in calculating this, we wrong estimate of H0. Also, if we made an error here in this form, we also have wrong H0. So people try to see the following.
It's still fine to neglect the radiation.
Oh, it's not fine. This is just an approximation. You're right. It should be included because we are close now. We're going close. I'm just writing here. It's very simple because I had shown this earlier, but you are right. It should be included here. So either there is an error here in this form, which will be included radiation as we said, and or an error measure RS. Most people, I mean, these are the two classes of model that have been considered. This is called, if you modify this one, you say you have a late time model. If you modify this one, using this integral here, you say you have an early time. So you can do anything you want. People have done everything that was possible. They have, for example, change this. In a very way, we put different dark energy here. You can change this. Or you can change it by putting dark energy at early times. This is so-called early dark energy. And so one can actually put here early dark energy and change this H of A, or you can put late dark energy and change this. Now, both of these approaches have big problems, have lots of fine tuning, and in fact, if you try to mess up with this thing, usually, but not always, you are in trouble because this thing is constrained very strongly by other probes, like supernova and baryon acoustic oscillation that we saw. So it's very difficult to probe this. It's not impossible. We had some interesting talks by Osgur here, which found some way with abrupt transition to bypass this problem. So this may have some potential to work. Also, this one here, it's difficult because you have to put it exactly just before recombination and not affect what happens after recombination. That's also difficult. You have to fine-tune things very much. Put the right time and make it disappear after recombination so it doesn't mess up with this thing here, with this integral. Lots of fine-tuning and difficult situation. So there is degeneracy between RS, H0, and EOG. It's probably that one of these will have to change. Of course, one can say, why not change the late time? Another approach is just to say that H0 that you measure at late times is wrong. So in that case, you don't have to change anything here. Everything is fine. Just find the error of the Cepheids. That's also a possibility. This is the third class of model. It could be systematic, but it could be also new physics. Close by new physics, Cepheids astrophysics, but it could be new physics. I mean, no one can exclude this possibility. So here I have a plot of this. How does the baryon acoustic oscillations occur? We have oscillations at the time of recombination due to pressure and gravity. And at some point, you have waves which are driven by the pressure of photons outwards. You see here, here's an edge of this is a wave on the last scattering surface. Photons press outwards. You have spherical waves which expand. After that, gravity wins, it shrinks, and there is an oscillation. At some point, as it expands, photons decouple because atoms form, and then photons are not coupled anymore. And so photons go away, and the spherical baryon wave freezes. This sphere has the size of the sound horizon at that time and can be measured on the matter of the large scale structure. And here is so initially we have expanding sound waves emanating from baryon gas perturbation driven by the photon pressure. At recombination, photons free stream, they decouple from the baryons, but so the pressure becomes negligible, and the spherical cells of baryons freeze there. And it's this thing that remains a standard ruler, which can be seen both on the CMB spectrum, and later on it remains there, and structure forms around that. And so we have another which affects the spectrum, various places, of course, not only one place. So the spectrum is affected, and we see this feature which gives us the information about the size of this object. So here is a picture of how this happens. You see, initially everything is coupled. We have dark matter with the black light, gas, that is baryons, the photons which participate, and of course we have also neutrinos which are relativistic and also decoupled. And so you see, what's happening? So you see that this expands, this is a coupling between photons, suddenly the photons decouple, the baryons remain there frozen, and eventually dark matter, this black thing, eventually eventually form structures around these baryons, and they form this characteristic feature on the large scale structure. So we can measure then this. This is in here, this dark matter, nothing happens to dark matter here, but eventually, because the baryons are there, the dark matter follows and forms the structure with this characteristic scale. So we can measure this with the baryon acoustic oscillation. So this is the idea of the standard rulers at late times. And so the next question is the following. How much time do I have?
You have 5 minutes.
5 minutes, okay. Next question is the following. Is it really, what if the problem is at late time? I mean, okay, we said we can change the Hubble expansion rate, we can change the time horizon scale to make H0 from the CFD to be consistent with the local scale. What if there was a problem locally? Now, let's assume, therefore, that in fact the CMB is correct. So this is exactly the correction. We have measured correctly the RS and the expansion rate, and assume that this is correct, and then use this Hubble parameter, which is obtained from the CMB. This is its value, from the southern horizon, use this to calibrate the supernovae. As I said, we measure from cosmology this combination, which is degenerate. So instead of measuring M from Cepheids and inferring H naught, let's say that we have measured H naught from the CMB and then we infer M, the absolute magnitude of the supernova. And what we would get then? We would get a value of minus 19.4 for this absolute magnitude, which is actually smaller than the corresponding values obtained by the Cepheids. So if the Cepheids somehow were wrong, and in fact M was to be smaller, there would be no Hubble tension, at least as far as the most precise probe is concerned. So, well, people have asked the equation and see what if this was wrong, and they have looked for systematics. Been lots of work to look for systematics that would make this number, Very hard work during the last 5-6 years. All systematics were found to be okay by many groups. What people have not spent time doing is look for new physics. What if there was some kind of real physics change which actually make these two make us think that this is this value? And it's likely because this is actually here measured at redshift Z outside of the Hubble flow, larger than 0.01. But this is measured at very local scales outside of the Hubble flow, where the Cepheids are there. So these are measured at different times, at different scales. So maybe at these times it had this value, and after that, after Z 0.01, obtained this value. I mean, this is not inconsistent with this possibility, because if this happens, there is no inconsistency. One is measured there, the other is measured there, consistent. But you have to assume some physics change that happened. So this is the M tension. And so we have now the corresponding thing with the local probes is the following. If we just, with the Cepheids, you start, you measure this from cosmology, you measure this from the Cepheids, and you go to this degenerate parameter here, you put this M here, assume that what you measured at the redshifts which are larger, assume that what you measured at smaller redshift is the same as in the Hubble flow, make this important assumption. And if you make this assumption, we go ahead and say that this, if we go here and plug in this M that I found from this Cepheids, this is the H naught. And you find this thing, 73.2, etc. Which 5 sigma away from this one. So it's an important, that's how people do. And then, of course, this larger, much larger 5 sigma with the CMB. And this is the H naught tension. But one has to notice here, what kind of physics change would actually make this change to this one at 0.01? The obvious thing to think is a gravitational transition. Because why? Because M depends on the gravitational constant. So there's an assumption here hidden that gravity is the same before and after Z is equal to 0.01. Could this assumption be violated? And this brings me to the hypothesis, the so-called M transition hypothesis we have introduced in a few papers during the last couple of years. And this is the hypothesis. What if the Cepheid absolute magnitude is, in fact, this value, correct? In this value, there's no systematic here, but the other part, which is in the Hubble flow, which is obtained from the CMB, these are the CMB points. This is the Pantheon plus points, Pantheon points actually, normalized based on the CMB, so it has, we put a minus 19.05 here. This is the MB obtained from the inverse distance ladder. And you see that this is measured here, this is measured here. Consistency, only if there's a transition. And so we actually, this is the idea here. And so we actually, this would resolve, if there's a transition here, would resolve clearly the Hubble tension. And as I said here, could also potentially resolve the growth tension, because if G effective decreases, then we have weaker gravity naturally, and this resolves also the growth tension, in principle at least.
And what would have to be the relative change in the gravitational coupling?
Well, it depends on the modeling. It depends how M depends on G. And that's not so clear, because lots of astrophysics enter in this question, because you have to understand exactly how does the M depends on G effect. The most naive, the simplest approach would be to say, let me show it to you here, because we have it, I have it, this, to say that L depends on the effective with some power B, which is a free parameter in principle, but if you assume the simplest case that L is proportional to the absolute luminosity proportional to the Chandrasekhar mass, then this B is equal to minus 3/2. This is simplest probably, the simplest case. That the Chandrasekhar mass is proportional to G to the minus 3/2. But there are other factors happening. But the simplest case is this one, because we expect that the mass, the critical mass where the thing explodes, should play a role in its luminosity, the absolute luminosity. So what is this power? It's this one, this power. If you assume that this equivalence is true. If you assume this, and this is a big if here, then one can show that the change of M absolute magnitude with mu, which is the G effective over G Newton before and after the transition, then you would need, because you need a delta M equal to 0.2 here, then you need a change of about 10% of G effective at this point. Now, is it a crazy thing to happen? No, because constraints, astrophysical constraints G dot, the time derivative, do not constrain delta G. Delta G is constrained only by nucleosynthesis to be the same as today, about 5 to 10%. That's the current bounds on delta G between now and nucleosynthesis. G dot, of course, is much more stringent, but we're talking about the transition here. And so G dot will be here 0, here 0 also. So this is not an issue. Okay, it looks like I don't have much more time to say, but how much time do I have? 0? Huh? 0. Okay, so I will then go to the conclusions directly. And here are the conclusions. Actually, let me show you something before the conclusion. So we want to reanalyze this FI data by allowing this transition. So this is the analysis done by Sue's group, which just analyze MB assuming it's constant. Now we have reanalyzed this and allowed MB to change at various distances. And one of the distances was, for example, 50 megapascals. If you allow MB to change, then these two last hosts, these are supernova hosts, now spontaneously come down to exactly what the supernova, or what the CB would like. This is spontaneous. So, of course, the error bars are very big. But this is an interesting one. Unfortunately, there are only 4 supernova in these two hosts. So that's why we have very large error bars here. But it's important to these 2 points to try. Of course, it's difficult to find new supernovas because they very rarely to appear in these distances. But once we have reduced the error bars to this point, actually this scenario could be either excluded or not really excluded, but because it's difficult to. Anyway, you see that there's an overlap here. It's addressed larger than 0.01. But anyway, it's possible to make a statement about this. So anyway, this is a model which can induce this kind of transition through standard tensor theory, through a first order phase transition, false vacuum decay. I will not have time to say anything about that. But so and here are the main points of this talk. Thank you for your attention.
Yeah, questions?
Wouldn't this also solve somehow the other problems you mentioned, like dipole problem?
Okay, that's an important point. Of course, I mean, ideally, what one would like to do is to solve simultaneously all these other problems. Now, the approach that I mentioned here, this has in principle the potential to address this problem because if it's a first order transition, you are off-centered from a bubble, blue physics, so naturally you would see some anisotropy. Also, the growth tension can be addressed because you actually will have a different G effective at earlier times. If it's weaker, we deal with the growth tension. And of course, you completely solve the Hubble tension in the context of this FIs, at least, using this approach. Now, it's difficult to address all these 3 tensions in the context of a model. There are very few models can do that, but there are some models which manage to address at least 2 of them, which means to address the growth tension, reduce the growth, and the Hubble tension. And okay, so at this time there is no clear evidence for any such simple model which will resolve simultaneously all these models, but at least that's the goal. The goal is to find a simple model with 1 or 2 parameters which will actually simultaneously address at least these 3 tensions. There are other tensions which are weaker in terms of significance, and so this is the basic goal, but so far we're not yet at this point to address all the stations at the same time.
What other effects would you expect from a change in G? Can you probe that?
Well, that's a good question. In fact, one other thing you would expect some astrophysical relations to also change. For example, the Thule-Fisher relation, the slope of this relation. We expect for these parameters to have if you group stars, if you group in different filters, you will see different parameters. Now, people have not looked for that. This is a very thing I've not very few people would dare to look. Even if you tell it to someone, why not look at this one? Say, why? Why should I even think to group the two stars into groups and look for this thing? So but we did that. Actually, we tried to the Thule-Fisher relation. We tried to split the sample in two parts, and we saw some hints, less than 2, about 1.5 to 2 sigma, about 2 sigma, for in fact a change of parameters at about 20 megaparsecs. That was one observation, but of course it's still answered. But the point is that the scenario is not excluded in the sense that you cannot really, you don't have enough error bars to exclude this possibility, but you cannot also easily verify it because there's not the error bars are big. But in principle, one has to look for this to find it. When people do not look for this effect, and it's important, I think, to try to have some physical searches which will actually look for this kind of effect. Otherwise, it will not be possible to find. But it's not easy to find because the uncertainties are large for this.
And locally, like in the galaxy or in the solar system,
Yes.
there was a passage.
Okay, yeah, in the solar system, if there was a passage, we would have seen it. So this is excluded as a possibility. If it was happening at the late times, of course, we would have seen. Now, at early times, if there was a passage, I have written a paper which would I mean, there has been some changes in Earth recently. We know, for example, the dinosaurs were excluded about exactly the time that this model could predict. About 150, about 70 million years ago, we had dramatic effects happening in the solar system and in Earth. We had an increase of meteorites, comets, etc. And this is an issue which, in principle, could be connected with these such events. I mean, these events cannot be true, but in fact, that's a possibility. So I've written a paper which actually discusses this as a possibility from change of gravitational physics during this environment, in this area. But again, the uncertainties are very big, so we cannot really say anything. But the thing is, we cannot also exclude this.
Any other question? Shall we get any question from online?
Actually, no, I don't see any answer. You will see it there.
I would say it here.
Yes, but so there's nothing in chat. So.
Okay. I have one question. Okay.
Just understood correctly. So this phase transition at around redshift 0.01.
Yeah.
I mean, the redshift range is actually coming from the fact that we don't have, you know, it's right at the limit of the
Exactly. It's not right. It doesn't have to be right at the limit. It can be any distance smaller than that. It does not have to be exactly at 0.001. We can look at all distances below this, because if this happened at any time, now we find evidence. Well, evidence. We have some hints for something happening at either 20 megaparsecs or 50 megaparsecs. 50 megaparsecs is in the right direction. At 20 megaparsecs, we find another small hint, but it indicates some raise of M rather than a drop of M. So it's probably not directly connected to this. But at 50 megaparsecs, in fact, a drop of M in the direction that we would like it to be. So it doesn't have to be at 50, it can be at any smaller redshift, so that, and that the Cepheid data would be able to give us this information. And in the Cephides, we find hints for some small hints from these two distances.
And new surveys, I don't know, SST, whatever, would be able to actually.
Well, these measure redshifts mostly, galaxy redshifts. So you need to measure astrophysical properties. So it has to go somewhere.
The statistics of the, you know.
You see a galaxy, and you see actually you can actually try to look at the color parameters of supernovae, like the way to standardize supernova, you use color and shape. There are two parameters when you have. So if these coefficients which standardize the supernovae were to be different at different ranks at different distances, then this would be an indication of a change. In fact, there's a paper recently, about a year ago, I think, by Radoslav Wojtek, I think, where he actually points out, in fact, this kind of effect. He did a very careful study of the color parameter of the standardization of supernova and found a statistically significant difference between the supernova in the second rank, which is where they are in Cepheid hosts, and the supernova which are in the third rank, which are in the Hubble expansion part. And so this is exactly the distance point that we want. The second rank ends at about 0.01, and the third rank starts at this point. So it's exactly, but of course he didn't really think to do a distance search. See at which distance does it really happen. I mean, he only looked at one distance, just compared the ranks. So I think I was talking to him in this meeting in Lisbon, and we agree that it's important to actually extend this and see what is the distance where this actually happens and how does this compare with this distance that we find here. You see this distance that I showed before, is here, which is about 50 megaparsecs. Is it really correlated somehow? Because it's a completely different effect. He looked at a very different effect and found this exactly a similar behavior. A change at about the same distance, 50 megaparsecs, independent. This is pure astrophysics. So there is potential. I think this thing deserves to be looked at least deserves to be looked at more carefully. I don't know if something really happened, but it deserves to be more carefully discussed.
Yeah. So you said that so the gravity is weakened, so you can solve the sigma extension.
Exactly. Yes, yes.
But then if the ZMST results we rely on, but actually you need again a much more stronger gravity. So then how you reconcile that?
I have no answer to that.
Okay, so if there are no more questions, so thank the speaker. We'll be done back at 2:30.
You're here, right? In the afternoon. Paulo wants to talk to you. Solution. And also me, I guess. Yeah, sure. Yes.
Just how do I stop here? I have to stop now.
Yes, just stop.